Welcome, everyone. Thank you for attending. Please, if you have questions, put it in the Q&A box and we will address those after the presentation. And now I will turn it over to Norbert.
Oh, thank you. And thanks for everybody for joining this webinar. So my name is Norbert van der Covering. I'm currently working in Oman for Occidental, otherwise known as Oxy. And this is work I'm going to present done together with Klaas Koster and Rob Holt. The title is A Skeptic's View of Vvaz and AVAz, velocity variation and amplitude variation with azimuth, and in particular, how we use this seam phase 2 unconventional Barrett model. Some of you may have seen some of this work before at a previous SEG conference or in the leading edge, but since we have a bit more time today, we'll go into a bit more detail and some recent updates, and hopefully we'll have a good discussion at the end. So let me go to the next. So I'll start with a brief introduction. I'm going to talk about the processing of the modeled seismic data. Then I'll dive straight into the azimuthal velocity and amplitude analysis and some related conclusions and discussions before I go to recent updates on work in progress. And we should have ample time for Q&A. So introduction. I think most of you would agree that knowledge of fracture density in the subsurface and its orientation or preferred orientation, if there is any, would significantly affect the reservoir development plans that you may have. Because if you could optimize that, that would be great. So, but the seismic propagation velocity in a fracture medium is faster parallel to the fractures and slower in the orthogonal direction. Think of it as like going up the stairs. That would be more difficult and slower than actually going the other way on one step. Consequence of this, both the reflection strength and the travel time should vary with azimuth. And in theory, these properties can be derived from seismic, in particular seismic azimuthal anisotropy. We do expect this to be challenging with complexity in the near surface, something that is commonly encountered in the Permian Basin as one example. We also have it in Oman and there are plenty of other places. So the objective of this paper and this research, or applied research, if you will, is to gain insight into the validity of onshore seismic azimuthal analysis, in particular velocity and amplitude variation with azimuth on the P wave, to see if those predictions can give us reservoir properties by testing it on a known model. So what better model than the II Barrett model, because that is an onshore unconventional model. It's well suited for these tests because it's fully sampled and it's mostly noise free. The noise is actually fairly easy to remove, and I'll show some of that. It does contain many key features and challenges present in unconventional plays of continental basins, such as complex near-surface region with buried topography. So we have some scattering of surface and body waves. And the stratigraphic overburden, which is created by geostatistical modeling based on the Yakima Basin in North America. It is aimed to have some realistic scenarios in there, like varying facies, faults, and meandering stream channels. That the reservoir section in this model consists of shale layers, and I'll have some images further on to highlight what those are and how they look. And those shale layers have geobodies or sweet spots, having high or low total organic content, and they are either brittle or ductile. So there are actually four types of geobodies, if you will. And those are actually based on real data, on cores and well logs from both Eagle Ford and Woodford in Oklahoma and Texas. So it's not like this is based on idealized or unrealistic properties. The model, the full model, does have orthorhombic anisotropy, combining VTI and HTI from top to bottom with varying properties, and I'll highlight some of those. It also has shear wave attenuation in the near surface to mimic partitioning of energy between surface waves and body waves. It also has major faults presence, which will be obvious later on. There has been some discussion in recent publications over the last few years about the validity of this model, and in particular related to the anisotropy values and the thickness of these shale geobodies. And we'll discuss and address some of these topics throughout the presentation, but we were happy to see that there was some discussion coming up in the literature. Here we have a kind of a 3D sliced view of the model where we can see the buried topography, the major fault here in the section. Hopefully you can see that. We have a stream channel a little bit shallower, and here we have a representation of some offset shale geobodies. So it is actually 10 by 10 kilometers, this model, and 3.75 kilometers deep. When we look at a profile, which is right at the center in the middle bin, so at 5 kilometers both ways, you see an extraction of the P and S wave and density, the basic elastic properties. So we go from shallow to deep, we get the first shale layer, the upper reservoir, an upper chalk, which is a high acoustic impedance contrast. Then we get another contrast, we go to the lower shale reservoir, and then finally we have the lower chalk. So these shale reservoir bodies are actually buried inside some impedance contrast. And this is an example through the center of the model. So this is 10 kilometers wide, of the exact properties of the known model as they are delivered. The first one here is the P wave velocity. So you see those high velocity chalks right here. And we also have some deltas of the VTI and HTI anisotropy. So this VTI property is gradually increasing with depth, but here it's kind of a discrete variation. The angle of the azimuth is also present throughout the model, but put constant in a lot of places. Now, I should point out that this VP is the basic elastic property, but that goes into the stiffness matrix, like the Vvaz and the density. So the orthorhombic elasticity properties for each shale body actually do vary based on those, because you have to compute the whole property matrix. So let's go to the model seismic data. So the processing from by now a few years ago. Actually not that long, but it's not current processing. So the objective of the first processing phase is to determine if the azimuthal attributes extracted from data acquired with ultra high density acquisition and a very high signal to noise ratio. Remember, the noise level is pretty low, to see if that could be related to known reservoir properties. And then in a positive case, subsequent phases would be run, which we haven't done, which will become clear. Subsequent phases were envisioned with added noise and data decimation to kind of mimic a more typical onshore nowadays acquisition geometry, and to see how far we could go in the decimation to estimate those reservoir properties. There is a reference below on the processing. So that classic data set, I'm not sure how classic it is because each shot has 1.6 million traces. So the fold is very high. Subsequently, the size is also not small. So not every processing shop can process this amount of data in a reasonable amount of time. We have retained all the traces for the noise attenuation, etc., until the OVT offset vector tile binning for migration. So the OVT bin actually for migration is 200 by 200 meters. And we did limit the offset to 4 kilometers, and the reciprocal OVTs were dropped, apart from a few as a test. We did have a nominal fold of 642. And finally, the CDP grid is 6.25 by 6.25 meters. So that's pretty dense. Here's an example of that classic data set. We have a shot gather. So we can see, nice signal. We have the first break, the direct wave. We see some other types of noise, backscattered noise, but in general, that noise level is a lot lower than the actual signal. And if we go through a time slice, you can kind of see that nice cone here. So there's no aliasing going on here, which is kind of nice. Yes, that is just a repetition of what I just explained, how to what bin size we went. So for the migration, we did a typical VTI Kirchhoff depth migration, as you would commonly do on the land, or onshore seismic unconventional these days. The velocity was lightly smooth from the exact model, the anisotropy as well. Speaking of which, the true epsilon and delta, they vary with azimuth. So we kind of took intermediate values for this migration. We will see some gathers, they are reasonably well flattened. And if we look at a near offset raw PSDM stack, you can see those major folds right here. Since the pre-processing is in time, this is not a depth section anymore. It's so from 0 to 2 seconds. And the first reservoir zone is right about here. And if we look, this is a line through the center of the model in line 800. And if we look at a gather right in the middle, so that's the gather at the center of the model. And this is sorted into or transformed into common offset, common azimuth or COCA. So you go from near to far offset 4 kilometers on the right with varying azimuth in each offset plane. You can see that the azimuthal variation of travel time gets greater and greater with offset. One thing I did forget to mention is that right here, I hope you can see, you see those little dots inside the seismic. Those were actually unintentional. They were an artifact from the model, the modeling. However, it's a good QC for the migration because they should nicely collapse. The signal should nicely collapse. The line I've indicated here is a 45 incidence angle degree mute line using the unsmoothed migration velocities. Remember, those migration velocities were already lightly smoothed from the exact model. And you can see clearly the effect of the high velocity chalk here. So that effect is quite large. But overall, apart from the azimuthal effect, the gathers are quite flat. Well, at least in this location. Now, at the time, we did do a test of VTI versus orthorhombic migration. So we have a few gathers with VTI migration on the left and orthorhombic migration on the right. And Yes, in places, the flattening and the signal is better in the orthorhombic migration. However, there will always be some residual move out from the migration. We cannot perform a perfect migration or a perfect velocity model estimation. In the case of orthorhombic migration, if you want to do that reliably, you have to estimate all those parameters independently, reliably, and that's still rather complicated. Now let's get to the azimuthal velocity and amplitude analysis after having processed this data. So first I'll go into the velocity and then the amplitudes. We have performed many tests, but finally we use the concept of layer strippings, meaning we want to address the fact that we assume that in the zone above our reservoir, there is no azimuthal anisotropy, or we think it should not be there. We need to remove the effect of that first before we can determine the effect of the anisotropy in the reservoir itself. So we want to flatten all the events above the reservoir as best as possible, remove overburden effects. And then we input those gathers to the azimuthal velocity analysis. Following the Grechka-Zwankin article, which I reference below, the generalized X equation, I use horizons to convert the azimuthal velocity from RMS to interval. There is a way to do that orthorhombically, but that is not applicable right now here. So on the left, we have that Coca gather repeated again that I showed you before with the 45-degree mute line. Here we do that layer stripping. We flatten the events above the reservoir, more specifically, not in the very shallow, because in the very shallow we have azimuthal anisotropy, but we don't have the offsets either to determine this time shift. So it's based on this zone here, indicated here. And you can see that those events are kind of flat now, but there is still a residual variation of travel time with azimuth. If you do that velocity analysis with azimuth, I'm showing you here the central inline for the center of the model again. The gather location is right here, what you see. And this is our first shale reservoir zone, the chalk, and the second zone. The property I'm showing here is the normalized velocity difference, which is basically velocity anisotropy intensity. So V fast minus V slow divided by V fast in the interval domain. So the values are, the scale is from 0 to 40%. So here, these yellowish red points, it gets quite high, that velocity variation. In fact, it's very high. Those are very high numbers, perhaps a little unrealistic. Now I can derive a map. I should go back and point out that the RMS property of the RMS map of this property is actually derived between these two black horizons, which defines that reservoir zone. If we go to that map, again, scale 0 to 40, just for shortness, I call this E, this normalized velocity difference. That central line was right here, and the gather you saw was right in the middle. The darker colors here are the known shale geobodies, which have anisotropy. And the thickest parts are the darker gray, blackish. The color here, you can see that here we kind of have three strips with very high velocity anisotropy. We have some border effect, and we have some other effects going on here. But this property doesn't have any resemblance to the known anisotropic shale bodies. Now, could it be that we just don't detect them? Some of them are too thin. So on the right here, I repeat this property E, but through opacity, I'm also showing the two-way time thickness of those geobodies. And sometimes the two are overlapping to form one thicker body, like here. This is the thickest one, up to 45 millisecond, which is just under 100 meters thickness. So some discussions in the literature say that this is not a typical shale body thickness, and of course we cannot see the VVSA. I would, however, possibly dispute that. I don't think 100 meters is that unrealistic for a shale body to be present and to have anisotropy. Sorry about that. I'm showing you a different line here, a different section, two parts where that velocity anisotropy is very, very high. In fact, it is so high, above 40%, that we have to be skeptical that that can be realistic, the anisotropy, that we can have such a velocity variation with azimuth. Let's then look at a few gathers, how they look. I repeat the coca gather, raw migrated. So this did not have the, that layer stripping applied. I'm just comparing raw gathers here, just to avoid any discussion. So you see that the travel time difference with azimuth and offset, by the way, right here. But we know that right in the center, those shale bodies are at its thinnest, and the anisotropy in these shale bodies is actually low. We will see that later. So we don't expect a very, very large Vvaz effect here. Whereas right here, it is higher. And this is one of the shale geobodies that does have large anisotropy. And we do see a nice large sinusoidal effect here. Before I go to the anisotropic gradient, let's look at the azimuth of the fast velocity. So in the model, if you look at a map right in this first zone in the middle, it's constant. I think it was 55 or 60. Don't remember exactly. But when I look at the azimuth of Vvaz, it's all over the place. And then the median is not even close to what it should be. So this seems to be a rather unstable property. So let's look at this in a bit more detail. Is there any correlation with the complex near surface? Because after all, that's where the energy starts and the waves start. So the way I look or represent the near surface overburden map here is an RMS value of the acoustic impedance, which I use as a proxy for reflection coefficients or amplitudes. And you can see these nice patterns here of that complex near surface. If I repeat the map on the right with the known two-way time travel thickness of the shale geobodies and that velocity anisotropy intensity, there's no correlation there. So that's kind of going down the wrong path then, it seems. That's not to say that this near surface cannot have an impact, but there is no direct correlation here. So let's go to the amplitudes. So we have tested several azimuthal amplitude analysis methods. we stuck on one method, which is basically the anisotropic gradient. I call it BANI, using the Fourier coefficient method. It's not that dissimilar from Ruger, but the Fourier coefficient seems to be applicable to higher incidence angles. The error is a little bit smaller. And that reference is right below here. We did test normalizing the amplitude, both azimuthally and with incidence angle above the reservoir, kind of similar to that layer stripping for the velocities, where we say in the overburden, we don't expect to have azimuthal amplitude variations, azimuthal and incidence angle. So we kind of normalize that to remove that effect. As a side note, the velocity, I'm not showing it here, but the velocity that you use for offset to angle conversion does matter. It can differ up to, I think, 6 degrees or even more incidence angles. So you should really use for each azimuth sector the appropriate velocity. The angle range used in this AVAZ is 10 to 40 degrees, as the near angles contribute little to the anisotropic term in the reflection coefficient. And I'll show you some map of that, why I say that. So let's get straight to the result. So I'm showing a map of the entire model again. Those same anisotropic shale geobody outline is shown. And the BANI, if we go to red and finally yellow, that means the anisotropic amplitude gradient is very, very high. We obviously have an edge effect here going on. And this is over that top shale reservoir zone. Unfortunately, there's no resemblance whatsoever. And that's a bit of a shame, but we'll go further into it. So here, just for clarity, we are outlining the thickest parts, but there's very little correlation, if any, to the BANI. Now, what should that BANI be? Obviously, there's various ways of computing that. You can go to effective anisotropy. There's different ways of doing it. The way I have done it is through using the computed reflectivity. I'm doing a fitting to derive the BANI with that Fourier coefficient method, and I'm using 12 azimuthal angle sectors. So 4 discrete azimuth sectors, and then each one has 3 incidence angles. And then I'm computing the RMS over that first zone again, which is kind of indicated here. That is that first zone. Remember, these are the base elastic properties, so you still have to compute the effective matrix. So it's a little unfair to say, look, the anisotropy in the middle of the model is very small. Yes, it is small, but it is true that right here, the BANI expected is very, very low, whereas in other areas, in the red, the BANI can be very high. But it is true that sometimes some bodies don't have a significant BANI signature. Remember that here is the thickest part for the shale bodies, up to 100 meters, and it does have a large BANI. But it seems that even this body we don't see in the BANI. Now let's go to that little side investigation on the near versus far angle contribution. If I go to the Vavrichuk and Pensick paper on P-wave reflection coefficients in weakly anisotropic elastic media. So this is the equation, a little daunting, but it's actually not that complicated. It's a P-wave reflectivity as a function of azimuth and P-wave incidence angle. Obviously, I'm only looking at P-wave. Obviously, the first thing is the isotropic part, but we're not really interested in that. We're not looking at the AVO as such today. So I'm only going to look at the anisotropic term. And in this anisotropic term, you see these A terms, which are basically coefficients from the stiffness tensor. So they do vary with azimuth. You see the azimuth appearing here and the incidence angle, but there's also the delta here, right? Because we are looking at reflection coefficients. So let's look at a map of this term. So I'm just going to look at the map of this term at one single azimuth, just for argument's sake. At an azimuth 105 degrees, with north being 0 and positive going clockwise. So when I look at near incidence angle 5 versus near incidence or versus incidence angle 30, and I scale those maps the same way of the RMS of that term over that first shale reservoir zone, the contribution of the near angle is negligible. And at the 30-degree angle, we start to see those the impact of those anisotropic shale geobodies. That's why in that Vvaz went for, or AVAz went from 10 to 40. Now, for these amplitudes, let's look, is there any correlation with any other properties on maps or things we have seen? So I'm repeating the RMS of the Biani map on the left. You see the two major faults here. And on the right, I'm showing you the RMS amplitude of the anisotropic turn of the model, but just over the near surface overburden zone. And this is computed at a single azimuth and incidence angle. It wouldn't make sense to compute this at the near angle as I just showed. So it does appear when I look at the outlines of some of these, that there may well be some correlation or some influence. Now, it's probably not going to be the only influence, and there may be a stack of factors, a stack of things going on that affect the Biani map at target, but there certainly seems to be a high correlation. Speaking of other factors going on, I'm also looking at the velocity model. We have the luxury in this case of knowing the exact velocity model, the V model. But here I'm computing an RMS map of the difference with the migration velocity model. I should note that this is the these are the verticalized velocities. So there is a difference in this velocity, which kind of mimics the near surface, that near surface map. So if I again make some outlines, I can certainly see some correlation there as well. Now, obviously, this is connected with the previous map and the other map. So there's probably a compounded effect going on. A point here is that we never know the velocity model exactly, and that can cause some problems as well, probably. Now, the conclusion as it stands now is that most unfortunately, we did not see any correlation, either quantitative or even qualitative, between the Vvaz AVAz attributes and those anisotropic reservoir bodies. We did see some correlation, however, to the near surface. And we assume that there is an effect of wavefront deformation in the near surface that is not fully removed during processing and the depth migration, which doesn't have a perfect model to begin with. So it is likely that a more costly and less sampled onshore seismic data set would be even worse. So we didn't bother to do those phases. Currently, even then, when this was first presented, but also today, we don't think it's worth running Vvaz and AVAz in the Permian Basin, where high near-surface complexity exists, and we typically have low signal-to-noise ratio. I say currently, because there might be a sliver of hope, and I'll come to that. A side conclusion, in accordance with modeled and theoretical response, the reflection strength of the near angles did not vary with azimuth, or it has very little contribution in the story. You could say we should have run orthorhombic PSDM, it might have been better, but you will have more terms to estimate, which you even know less about. And those errors will certainly propagate. Now, certainly that surprised me because earlier on in my career, I thought, hey, this is working, but it may even be upsetting. But the process data is available through the SEAM consortium, as is the model itself. So you can, if you don't like the processing, you can do your own processing tests. You can also do your own Vvaz and AVAz tests with the process data, with your favorite workflow. So this is actually the link, or you can just do a search on the SEAM, on the SEG site. So it's also an important aspect because many times we have proprietary data, we can release it, you cannot do your own research on that same data. And this is mentioned in the leading edge by one of the then presidents, vice presidents, that as much as possible, the data should be released, and the SEAM models are perfect for that. And we have provided the process data to that consortium. Now, let's get to the little update before we go to the Q&A. Given some points that were discussed and some things that there is some uncertainty about, we have gone back to some of the processing. And that's what this section is about. So we are addressing the concern of the statics, which I will come to in a minute. Oops, that's wrong button. Right, then there is the deconvolution, as well as some of the surface consistent amplitude corrections. So we are actively doing this today. I don't have any final results, certainly not the impact those steps have on Vvaz and AVAz, but hopefully that will come in the not too distant future. But we will certainly assess the impact of this reprocessing, if you will, with paying attention to these steps. I would like to point out that during the processing, it can be challenging to really quantitatively assess the impact of these surface consistent processes, especially amplitude corrections, decon. How do you assess those? How do you really QC those in detail? Because especially if we go to AVAz, the things we are going after are small, the effects. We are looking at a gradient of a gradient, basically. So you would almost have to go through the whole migration flow and then assess that every time. However, there might be some other ways, like quality factors, you can look at it, but it remains a little bit qualitative. So let's go to the first one, the refraction statics. This is ongoing work. So on the left, I have a source map on the right, a receiver map. It's on the same scale. It's just that when they did the modeling, they extended the receivers beyond the 10 by 10 kilometer model. So that's why they you see the same colors. It's just repeated. The scale is from -7 blue to +7 millisecond for both. And these statics are not that large. It's not what is typically seen on the land processing, it seems. That's because of the minimum P velocity in this model is not as low as you can encounter in reality. So the statics, these refraction statics are not deemed to have a very large effect. Now let's look at residual statics, just a few gathers, CDP gathers before applying these residual statics. And then I'll try to flip slowly back and forth a few times. Hopefully you can catch the update. So in our zone of interest, yeah, there are some minor differences. Is that enough to cause a difference in the end result? We don't know yet. Perhaps the effect of the earlier statics, residuals, and the decon and the amplitude corrections, perhaps all of those combined are large enough to cause a difference. Speaking of surface consistent amplitudes, on the left we have the source map again, on the right the receiver map for the full model. And we have the measured source and receiver strength. And you will see obviously that it looks a lot like some earlier maps we have seen of the new surface geology. So these really are scalar factors. So the green here is 1. Red is higher, blue is lower. Possibly these corrections are not as large as you would typically see in a real data processing project. Nevertheless, there are some variations there. I'm only going to look at the sources right now, but then split by frequency. So if you want to balance those in a self-consistent manner for the sources, look at the variation by frequency. So we have 10 Hertz on the left and 36 Hertz on the right. Obviously, we have more maps, but I'm not showing everything. You can see the variation with frequency because the color scale is the same. And that is probably not insignificant. And here the surface consistent decon may have an impact. So let's look at the source amplitude balancing at 10 Hertz for argument's sake. And at this Biani map I showed you earlier, and it's obvious that there is some correlation. You can see in general the factor is higher in the south, if you will, more bluish in the north. And here it's quite a lot lower, 0.7 almost. And you can see that in general here the BN is higher here, where this is actually blue and lower. So hopefully we are onto something here. Speaking of decon, let's look at a few shot gathers. So the animal is applied to the shot. This is our zone of interest. So again, I'll try to go back and forth a few times. The decon does do something. Whether it's enough remains to be seen. So that's enough about the updates. It's almost 5:45, so we can have 15 minutes for Q&A. But before that, I would like to acknowledge my co-authors, but Oxy in general for allowing us to do this and having the funding, and then the SEG and the SEAM for inviting me to speak today. in-depth geophysical for the processing at the time, and Michael and Carl for some personal communication and clarification, as well as AGT, who also clarified a few things, and land seismic noise specialists with whom we are working currently. So with that, I'm ready for some Q&A.
Norbert, it looks like we have a couple of questions in the chat. The first is, did you look at how internal thickness impacted your ability to extract reliable azimuths properties?
Oh yeah, I can see it now. Okay. Yeah, okay. Well, the azimuthal properties are actually not reliable, right? So it's in none of the maps. In terms of thickness, yes. Well, I addressed it up to a point doing that RMS to interval conversion horizon-based, because I have also done it sample by sample with smoothing and all that kind of thing. So yes, we did, but currently none of them are really reliable, but it's something we can revisit once we have the new processing. But for the velocities, yeah, certainly sample by sample wasn't very good. So I'm reading the next question. You think of any effects in the data which would have been helpful for your study but were not modeled in the input data provided by SEAM? Maybe, I think actually there are other data sets with other noise, more noise, different types of noise that could be useful. We can also add it ourselves. Then the next one, would it make more sense to extract VVAZ effects along events rather than time slices to remove residual velocity effects from the overburden? Actually, I did the VVAZ using the horizon, so it's horizon based. And then I presented RMS maps, so it's not time slice. And I have removed the effects of the overburden through that layer stripping. Maybe I wasn't very clear on that. Speaking of which, that next question is correlated to that. Is the layer stripping like a trim static or a VVAZ approach? It's like a trim static, but I'm keeping it constant. So I'm only applying one time shift to the whole trace, because otherwise, I think you create problems. You don't know anymore what is happening. There's one question in the other window. What about multiples related to shallow properties of the model, even surface related? No, that is currently not separated out. Yeah, we assume there are no multiples. Yeah, but it's true. That's a good point. That's another thing. Then there is another, maybe consider starting with a homogeneous overburden model to see in a very simple case. Actually, I think those exist in the literature. I understand the question, but I'm almost like, what is the point? Because this is a realistic permeable model. There is no homogeneous overburden, or rarely. But yeah, it's a fair point. You mentioned, I'll make sure I catch the right question. Gabrielle, looking forward to the self-consistent processing. Yeah, okay, I look forward to it too. I kind of hope it works. I remain skeptical, but You mentioned the difficulties of a fully anisotropic PSDM. Yes, we have tried orthorhombic and it doesn't completely flatten. And it's not easy to estimate all those 9 parameters or even more. Because often a relation is enforced between some of them. Did you consider simply measuring time thickness of the reservoir varying with azimuth for fixed offsets? Not directly. No, yeah, in a few cases we have, yeah. But I would say measuring the time thickness. That should come out in the velocity analysis, I think. But I haven't measured the time thickness directly. That I would have to think about that a little bit more, because that's you would have to do a bit more picking, or yeah. Okay, I have to think about that. Then Davis is saying extraction of azimuthal anisotropy parameters on ocean bottom. As you get thicker intervals, semi-reliable attributes. Yeah. But yeah, okay. I've personally worked on an offshore case where it did work. Because, well, for various reasons, but yeah. If we say it only works in thick enough units, I mean, why wouldn't 100-meter thick shale body be thick enough? That's extensive. I mean, if we can't even do that and we make all these claims that it does work, then yeah. But yeah, it's a fair point. Time from top to base reservoir reflection takes up many composite attributes like velocities. So yeah, I'm not sure I understand that question or comment. Certainly the velocity has lower resolution than the amplitude, yes. Okay. Okay.
Okay, Norbert, I think that's all of our questions for today. Thank you everyone for attending.
And I think the recording will be available on the website later on, right?
Yes, the recording will be available on SEG Live.
Excellent. Well, if anybody has anything, you can find me on LinkedIn or whatever. Always happy to have a technical discussion.
Wonderful. Thank you, Norbert. Thank you, everyone.
Thank you.